When you're evaluating arc length and area in parametric form, it's going to change the equation slightly because you're going to be looking at this from the perspective of being with respect to t instead of with respect to x. So arc length in parametric representation is going to be the integral from a to b of the square root of f prime of t squared plus g prime of t squared dt, where x equals f of t and y equals g of t. And the same restrictions go as far as, this can get complicated or it can be really simple. It just kind of depends on the problem. So with this one, I've got x equals 3t plus 5. So dx over dt, or f prime of t, is going to be 3. dy over dt for the 7 minus 2t would be negative 2. And we're going from t equals negative 1 to 3, so s is going to be the integral from negative 1 to 3 of the square root of 3 squared plus negative 2 squared dt, which is just a constant, so this is really the integral from negative 1 to 3 of the square root of 13 dt. So the square root of 13 gets multiplied by t, and this goes from negative 1 to 3. So we have the square root of 13 times 3 minus negative 1, which is going to be 4 square root of 13 for this one. Now for this example, I've got x equals 6t squared, so dx over dt is 12t. Y equals 2t cubed, so dy over dt is going to be 6t squared. And that goes from t equals 0 to 1. So s will be the integral from 0 to 1 of the square root of 12t squared plus 6t squared squared with respect to t. And you can see that this is going to be a much more interesting integral. So the trick here, I'm going to go ahead and multiply this out, and that'll be 144t squared plus 36t to the fourth. And keep in mind that I cannot break up this integral with addition, but I can potentially with multiplication. So what I'm going to do is I'm going to recognize that both of these are divisible by 36, and they also contain a t squared. So we'll make this the square root of 36t squared times the square root of 144 divided by 36 is going to be 4. And then the 36t to the fourth divided by 36t squared is t squared. And this will be 6t, since we're looking at t between 0 and 1, times the square root of 4 plus t squared. Now this is really nice because we can actually allow our u to be 4 plus t squared, which will make our du be 2t dt. So I'm going to bring out the 6 and make this 4 plus t squared to the 1/2 dt. And we have everything we need except for the 2, which is really easy to just multiply in there. So this gives me 3. We've got the integral of u to the 1/2 du. So I'm going to make that 4 plus t squared to the 3/2 divided by 3/2. And that's all going to go from t equals 0 to t equals 1. And of course, if you prefer to, you can always convert the bounds and not go back to t, but this is just how I like to do it. So I have 3 times 2/3, so those 3's cancel, times 4 plus t squared to the 3/2. So we'll have the square root of 4 plus 1 squared, so that's 5, and that's really not a square root, sorry, it's to the 3/2 power. So 4 plus 1 is 5 to the 3/2. And then 4 plus 0 squared is going to be 4 to the 3/2. And the only thing we can really do with the 5 to the 3/2 is make that 5 square root of 5. But we can go ahead and make 4 to the 3/2 8, because that's 4 square root of 4, which is 8. So I get 10 square root of 5 minus 16. The area of a surface of revolution has also been updated for parametric representation, and you can see what the what the formulas look like here. You've got 2 pi times the integral from a to b of either g of t times the square root of dx over dt squared plus dy over dt squared dt, or you may have an f of t. And basically the only difference is, are you revolving around the x-axis or the y-axis? So this is actually a little bit more simple than what we were doing before in rectangular coordinates, or in rectangular representation. So x is f of t, y equals g of t. If you're revolving around the x-axis, you use the y function g of t. If you're revolving around the y-axis, you use the x function f of t. Now, you may see some that say use a graphing utility to approximate the integral. We are just going to cross that out because we are better than that. We know how to integrate this stuff without having to do that. So keep in mind, we want to actually integrate. We don't want to use graphing utilities to do it for us. So I'm going to find dx over dt, which is 3. dy over dt, in this case, happens to be 1. And s is going to be 2 pi times the integral from 0 to 4 of g of t, because we're revolving around the x-axis, so we'll put t plus 2, times the square root of 3 squared plus 1 squared dt. Now this is your favorite scenario when the whole square root thing ends up being a constant, because I can just go ahead and bring out, I've got 2 pi, this will be the square root of 9 plus 1, which is 10. And then we're just left integrating t plus 2, which is really simple. So I have 2 pi square root of 10 times t squared over 2 plus 2t, going from t equals 0 to t equals 4. So I get 2 pi squared root of 10 times 4 squared over 2 plus 2 times 4 minus 0 squared over 2 plus 2 times 0. So that gives me 2 pi square root of 10 times 16 over 2 plus 2 times 4 minus 0, of course. And that's 2 times 16, which is 32 pi square root of 10. And that will be my surface area, so that's going to be units squared. Now keep in mind, any integration technique that you've learned up to this point may appear in these problems. I try to keep it pretty simple, but you could end up with a trig substitution or something a little complicated in here. So don't lose heart, just go back to your chapter 8 notes and you'll be fine. Now this one is given to us in terms of theta, but we're okay with that. That's not going to stress us out. Everything just gets converted to theta where you would normally have a t. So in this case, if I have cosine squared of theta, and I want to find dx over d theta, u would be cosine of theta, and x would be seen as u squared. So dx over d theta here would be 2u times u prime. U prime with respect to theta is negative sine of theta. So this is going to be 2 times cosine of theta times negative sine of theta, or negative 2 sine of theta cosine of theta. Y equals cosine of theta, so dy over d theta is just negative sine of theta. And we are revolving this according to the instructions about the x-axis, so we're going to use the y function as our multiplication. So s is going to be 2 pi times the integral from 0 to pi over 2. Y is cosine of theta, and we'll have the square root of negative 2 sine of theta cosine of theta squared plus negative sine of theta squared d theta. Now this may look really intimidating at first, but I promise you it's not going to be as bad as you think. We're just going to have to do a little bit of trig. So I've got cosine of theta. I'm going to go ahead and multiply this out and get 4 sine squared of theta cosine squared of theta plus sine squared of theta all d theta. And then what I'm going to do is I'm going to factor out the sine squared of theta. So I'm going to have 1 square root of sine squared of theta And here I'm going to be left with the square root of 4 cosine squared of theta plus 1. So this, of course, is going to be sine of theta cosine of theta, when you take the square root, times the square root of 4 cosine squared of theta plus 1 d theta. Now, in the best case scenario, we could allow our u to be 4 cosine squared of theta plus 1, which would require du to be 8 cosine of theta times the derivative, which is negative sine of theta d theta, or negative 8 sine of theta cosine of theta d theta. And it just so happens that we have everything we need except for the constant negative 8, which I'm just going to plop right down there to cancel it out. Okay, so now we're rolling. So we have negative pi over 4 times the integral from 0 to pi over 2, and keep in mind these are thetas, of u to the 1/2 du, and that's something we know how to work with. That gives me u to the 3/2 over 3/2. So I'm going to multiply by 2/3, and I'm going to have my 4 cosine squared of theta plus 1 to the 3/2 power, and that all goes from 0 to pi over 2. The trig is going to be a little bit messy, not going to lie to you, but we can handle it. So canceling out constants, I get negative pi over 6. Here I will have 4 times cosine of pi over 2 squared plus 1, and that's all raised to the 3/2 power, minus 4 cosine of 0 squared plus 1 raised to the 3/2 power. So cosine of pi over 2 is 0, meaning this first one is 4 times 0 squared plus 1 raised to the 3/2 power. Cosine of 0 is 1. So we have 4 times 1 squared plus 1, all raised to the 3/2 power. So this is negative pi over 6 times 4 to the 3/2 power minus 5 to the 3/2 power. 4 to the 3/2 is going to give me 4 square root of 4, which is, actually, you know what? This should be 0 because we have 4 times 0 plus 1. So this should be a 1 to the 3/2 power. Makes that a lot easier. So I have 1 minus 5 square root of 5. Now remember, anything raised to the 3/2 power is basically the square root of it cubed, and so that's why you end up with that 5 square root of 5. You can leave it as 5 to the 3/2 if you prefer. You'll see that some people will swap the sign in here and just make this 5 square root of 5 minus 1 and keep that as a positive, and keep the outside positive. I would accept either one of these perfectly well. Nothing wrong with that. But there you have it.